up to this point, you have looked at what AC is and how the current looks like, such as this simple circuit where I connect an AC power supply to, let's say, a resistor. So we can see that the AC power supply is going to cause an alternating voltage, which you can see on a device like a CRO, like this one. So make sure when you do experiments, you want to measure voltage of AC or frequency, use a CRO, because that's the one that will give you this nice oscillating kind of pattern. Oh, I've missed out there. If you use just a normal voltmeter, you're going to see a lot of numbers and you won't be able to read it. Look at this. It's oscillating. You can't read it with a voltmeter. So make sure whenever you're doing circuits, CRO, especially AC circuits, please use a CRO. Anyway, our dilemma and problem for us is today. So we have decided that AC is a great way to transmit power. But then, when you come to your house supply, like your phone charger, your calculator, your whatever you want to charge, they actually only need a DC supply. Like these circuits in your computers, in your devices, in your phone, only can take a DC. But this is AC. Look, it's oscillating up and down. How do you convert AC to DC? You see the arrows? They keep changing direction because it's alternating. One moment go forward, one moment go backwards. The current just keeps changing. How do we change? That's our question for today. So the component that you need to remember from your AS is, remember the thing that only allow current to flow in one direction? That thing, my friends, is called a diode. And the symbol that we use for the diode is this triangle, pointing in the direction that current is allowed to flow. So as long as there's current flowing in this direction, good, it will allow current to flow through. If current is trying to flow in the opposite direction, no entry, cannot allow to flow through. So this is called a diode. Let's do a bit of recap of how a diode works again. This is a bunch of DC circuits, but can you look and see which bulbs will turn on when you have closed a switch? Look at all these diodes. Okay, so how do you deal with this? You can look at the battery first. Positive, negative means the current will come out through here. And then, we close the switch, right? Where will the current flow? Will it flow down to B? You look very carefully. If you say current flow down to B, but then A, cannot, you need a closed loop for current to flow. So current will not go down through B, but it can go through A because the diode will allow it to pass through. Something like that. So the first one, A will light up. Let's look at a few more. How about C and D? Let's try. So positive here, negative here. Let's see, current need a complete loop. Can flow here. Nope, not through there. These are all very high potential. This whole area, high potential. Come out of the battery bar. Then it will go to lower potential. But the only way it can flow is down here. So your potential drop. This one, the whole potential drop. Which is the same as the battery's EMF. Drop down. Okay, now can return to battery. So our very nice C will light up nicely. D, unfortunately, no. Sadness. Because you're going from high potential to low potential on this side. So current can't flow backwards up to high potential. It doesn't work that way. Okay, let's look at the other two. Where will current flow? This one is positive to negative. Will current even flow? You see, got a problem. Current try to flow this way. But there's this no entry that's opposing. It will not let the current flow. So unfortunately, nothing will light up. The next one. Will this one light up? If we close the switch. We have another problem. Current try to flow, cannot flow. So none of these would light up, which is very unfortunate. Okay, so make sure you know how diodes work because that will be important in this section. So if you have a current flowing in the direction that the diode allows, such as this case that I draw up there, this is what we call forward biased. Forward bias, where the diode allows a current to flow through it. Reverse bias is if your current is trying to flow in the opposite direction. We have a problem. Cannot. So although it's trying to, it cannot. So this is called reverse bias. For just recap a bit from AS a bit. Okay, so what will this setup do to the circuit? Alright, so let's say we measure the output. This is what we call the input from an AC signal generator. The output we're going to take across the resistor. You can put a voltmeter, put an output, connect to other device. What would you say? We take a voltmeter, measure the output across the potential difference across the resistor with a value of R. How will the graphs change now that we have put that in there? So let's label all the things down together. We have an input voltage from the AC power supply in units of volts, and over time, this is how it looks like. So you have some positive, negative input. That's what the AC is doing, very much like the simulation we looked at earlier. So you're going to have this positive part of the current, negative, positive. Once you put a diode, what happens to this? All the reverse bias become no entry. It will not allow the current to flow backwards. Only can flow this way. Whoops, wrong color. Green color. Only can flow this way. Anything backwards cannot already. So when you draw the output voltage across this resistor, it's going to be chopped off. The negative parts will be chopped off. So down here, you see, so this is your input. Let's draw the output voltage. So output is going to be chopped off a little bit. So the positive part is a go. Sure, please pass through. Negative part, no go. Positive part, go. Negative part, no go. So your current will just be this part where the diode allows it to go through. A lumpy little thing. Okay, so we are pretty happy. We have all positive only, positive current in one direction. Voltage is only positive, but we're like, something is not quite right. You know, our goal of getting DC, our ideal DC, is a nice battery straight line. You know what I mean? The ideal DC is going to look like this. But how are we going to get that? This is lumpy. This is not even a straight line. How can we go from this lumpy thing here to a nice straight line kind of DC? That is the next part. By the way, this is what we call a rectified AC. Or rectified voltage. I just call it rectified AC lah. So rectified means no positive, negative, positive. No. Only positive in one direction. So let's look at ways where we can smooth out this thing. This is what we don't want because it's lumpy. So now if we look at a circuit setup, like what we saw, we throw in a diode, current can only flow in one direction. You look at this, the yellow charges, they only can flow clockwise. The negative part completely chopped off. So you can see that over here. No negative parts. Now, if you have, can you think of one component that can help you, store some kind of energy so that when nothing is flowing, it can discharge? Because you see, there will be a moment in time when nothing is moving in the circuit. Because that part of the circuit has been chopped off. No negative. So during this time when nothing is moving, can we throw some component in to store energy so that we can release it when it's needed? Ring a bell, store energy. What components store energy? If a capacitor came to mind, congratulations. The answer is the capacitor is the next component we can add into this circuit to do some smoothing, to smoothen the lumpy graph that we don't want. We want a nice smooth DC as much as we can. So how do we add this? So you're going to add a capacitor in parallel with the resistor or the whatever you're measuring the output across. Okay, remember we are measuring output across this resistor by the connecting more wires and pull it out or whatever it is. So you have an input voltage from the AC that is alternating and output. Now this capacitor will have some capacitance C and this one is some R. This is called an RC circuit. Okay, how does a capacitor do its work and help us store energy and smooth out the thing? Let's say in this first part, positive is here, negative is here. Does current flow through? Yes, current does flow through. So we have a current that can flow through the diode. Now when current comes here, what will happen is some will go down to charge the capacitor and some will go over to this side. The capacitor will charge pretty quickly depending on its capacitance, but let's assume it's fully charged. So we have all this positive charge sitting here, separated, not store. Almost said the word store. Positive charge all sitting right here. You can assume it's quite charged, fully charged. It's storing energy. Okay, the rest of the current will go through the resistor as usual. This is the first part, first stage, when the capacitor is charging. So I'm going to write here, capacitor charging. When there is current in the circuit. Okay, remember this is a half-wave rectification. So only half of the AC will be generating a current in the circuit because the other half is cancelled, chopped off by the diode. Actually, we can add another diode here to give extra protection. Sure, let's add another one here. Why not? Okay, so this is the first half, capacitor is charging. Now, there's a certain thing you need to know. How does the capacitance affect the energy stored? So when your capacitance is large, that means there is more energy stored in the capacitor. Why we want to store energy? All right, because later there will be no current. But you want a consistent current flowing through your resistor. We're trying to have that as consistent as we can. Okay, so first part, charging, capacitor will store the energy. You see the orange color all stored there. When the capacitor is fully charged, there will be no more current flowing through it already. So it's just like that. It's just chill. Just stored, chilled, sitting there, like a power bank. What happens when we go to the other part where the AC is now reversed? The current, the voltage, everything all reversed. Now that occurs when the input AC voltage has changed direction. So now negative is on top, positive at the bottom. So current will try to flow this way, but really cannot. You cannot. I mean, battery is trying to push, AC is trying to push, but no current can flow. So it's pretty much a dead circuit. But don't forget, we have charges stored on this capacitor. Well, not charge, energy stored on this capacitor, a certain potential difference. So now this capacitor will act like a battery. It stores up all this energy. All right, discharge, boom. So this next stage, when the AC cannot push a current through this circuit, the capacitor will do its work and discharge across the resistor. What am I saying? Discharge through resistor. So this one is a current from charge at the capacitor plates flowing through like this and go back to its original other plate. So here you see there's a tiny little current loop already. Yes. Is the current through the resistor the same? Check and see. In the beginning, the AC current pushing down. Correct, top to bottom. Now the capacitor current, top to bottom. Okay. So the polarity, the sign is correct. Nice. So this is the cycle of capacitor charging, capacitor discharging. It's just storing energy, and when the AC cannot give any energy, the capacitor will be the one to discharge through the resistor. To see this charging and discharging cycles and work, I'm going to use a simulation with a DC battery. I know it's a DC battery, but hey, now you can only let current flow in one direction because the diode has chopped it off. So why not? So I'm going to connect CRO voltmeter across here. And notice what happens when I let current flow. Got current, then no current now, nothing. So it's a very sharp spike. Got current, suddenly no current. Got current, suddenly no current. Now, of course, when you're using an AC power supply, it's not square. It'll be nice sine wave, increase, decrease, increase, decrease. But now, it's a simulation of what AC will be looking like. So how do we smooth out this thing? Here comes the capacitor. So I'm going to connect this capacitor right here. So in the first part, when I engage the battery, so when there's current coming in, yes, there's current flowing through the resistor, but the capacitor will be fully charged. Watch what happens when I disconnect this circuit. We still got current flowing through this resistor, but it's from the capacitor now. So now, if you see I do the on-off pulse, look at the CRO here. What do you see? It's not any more square waves, but it's this curve that decreases, and that is the curve from the discharging capacitor. It's smoothing out the squares. It's making the, the lumpy thing smoother a little bit. So, this is how it works. Capacitor charge, capacitor discharge through the resistor. So the capacitor is adding like a cushion to store energy and discharge energy as we need it to. And that's called smoothing in action. So let me add a quick reminder that this is the current not from the AC, because AC is blocked by the diodes already, but current from a discharging capacitor in parallel to R. There. Good reminder. All right, so how will the output look like now with a capacitor there doing its charging and discharging? So rectified is going to be this green color graph. Now if we add a capacitor, you will have something like this. Zoom, 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 increase. But the moment it starts to decrease, the capacitor begins to discharge. Ooh, so it smooths out a little bit. And then, it's charging again. All right, sure, let's charge up. And then you, discharge. So the graph will no longer be a hump, flat, a hump and flat. It'll just be going up and then slowly discharge. Go up and slowly discharge. So this part, let's label it with, what color shall we label? Let's use orange. this whole part is the capacitor discharging. That's why you have that smooth curve decrease. Whereas the first part here is from charging. Capacitor charge, okay, get ready. Then when there's no current, the capacitor, okay, I step in, I'm the emergency. Here, take all this energy. Here, resistor, smooth out a little bit. So this is what we call a rectified plus smoothened AC. So you have rectify and you have smoothing of your AC. So if you can adjust your values just nice that you get almost a straight line. Remember, the ultimate goals is to get a voltage or current that is a DC. DC means perfectly straight. This is not perfect, I know, but it's close. We're getting closer. How do you make it more smooth? Well, there's a few ways you can do this. Number one, you could change the capacitance, like I mentioned here. If you have more energy stored, you can keep more, and then when there's no current, you will be the one to release all that energy to the resistor. So yeah, you could increase your capacitance. So if you do that, you will have another curve, such as this red one. Wow, I barely lost much energy. So this curve is very much more smoother, and this is when you have a large capacitance to store more energy. More energy to store and release. But there's another way, and that is by changing the resistance. Resistance of the resistor. So this one, what affects the discharging of capacitors? You remember a little bit from your capacitor chapter. Let's review a bit. So how do you change the discharging? The discharging curve looks something like this. So the potential difference across the capacitor is this declining exponential decay. Right? And if you change, who is it discharging through, by the way? Alright, you discharge through the resistor. So the resistor actually controls your current. How much is the current flowing? So I'm going to put a label here. This guy affects the current, because VIR, affects current, and therefore the discharging time. Because current is rate of flow of charge. If current is very large, you can discharge very quickly. So maybe make that a note somewhere on your notes there. Okay, so resistance here can affect discharging time. So how would that look like? Well, if I say I make a very large resistance, then I have something like this. So this will be a much slower discharge. It takes much longer to reach zero. So like that. Okay, so this is if I use a large resistor. So you are discharging through a very large resistor, and hence you have a very small current. And current is what? Rate of flow of charge. Remember, discharging is about all these charges returning back to their original position where they were. So what if you have a very small resistor? Well, small resistor will be the other way. So small resistor, maybe somewhere here. Pew, straight away discharge already. This is if you have a small resistance. So the capacitor will discharge very quickly because you have a large current, and large current means a lot of charges, rate of flow of charges is very high. So you see, we can achieve a better smoothing if you use a pretty large resistor. So I'm going to put another note here. A large resistor, and this makes a longer discharging time. Something like that. Okay, so two ways you can increase the smoothing by changing C and changing R. They will ask you to sketch this in exams sometimes. So write a final reminder for ourselves at the side here. No space, but the resistance affects current flow. So affects I, which is charge flow, rate of flow of charge, and hence, I think I already wrote this up there, never mind lah, and hence it affects discharging time. Okay, now we are kind of satisfied, but there's another problem here. We haven't achieved our perfectly straight V graph. There's a lot of variation. This is what we call variation. See, all the up, down, up, down. This is what we call variation. There's still some variation. Sure, you can achieve a pretty good smoothing, but it's not ideal. It's still not a straight graph. We want even better. And we have another problem. We lost a lot of the negative part. You see this whole negative part? That's a lot of energy wasted, you know, but the diode has chopped it off. So if you draw a power graph, once you rectify, you're only going to get a bit of power, then no power at all. Some power, no power at all. Well, of course, if you can smooth it, you will smooth the curve out lah. So you will get something like pew, pew. But the point is, you have removed a big part, half. You have lost half of the original AC current. That's not great too. So the next video that you see will think of a better way how we can make sure we make use of the other part that we lost. So this highlighted part. That is called full wave rectification. This, what we looked at, is called half wave rectification. So half of the wave rectified. We have just removed the negative. We have the positive with us. We tried our best to smooth it and get something like a AC. This is our goals. Hashtag goals. We're trying to achieve this a nice DC, flat DC. So main takeaway is, one last thing to add on is, we try to get AC to DC by rectifying it. So this is what we call the process of rectification. And what we learned today is the idea of smoothing. So I'm going to write here. You kind of have to know what this means. Explain what is meant by smoothing. So you must make sure you know how to explain. So what is smoothing? Smoothing is just what we call a reduction in variation of what? Variation of the output current or voltage. So yes, we want to go from AC to DC. DC is not supposed to have variation. So this one, no variation. This is the goal. Like I keep saying, goal, no variation. So just a straight line. No up, down, bumpy. So we'll try our best to smooth with capacitors and resistance value. So capacitor is our friend here. Rectification, our friend is the diode. Okay, and for smoothing, our friend is the capacitor. Oh yeah, I should draw the logo. Okay, capacitor. Okay, so in the next part, you will continue your adventure of how to do that, how to solve this problem and get it as smooth as you can. Do not lose any power, maximize the current. So that's all for this video. See you in the next part where we look at full wave rectification. That's all. See you then lah. Bye bye.